Hey everybody, Mr. Troy here. I got a quick video for you on even and odd functions. It's time for math with Mr. Troy. The definition of an odd function is one that is symmetric about the origin. The definition of an even function is one that is symmetric about the y-axis. A function that is neither symmetric to the origin nor symmetric about the y-axis is neither even nor odd. While all the examples in this video are about polynomial functions, any function type can be even or odd. An odd function will have the property that f of the opposite of x will be the opposite of f of x. So it has the property that the negative 1 times x will leave the function. So for example, when I look at this function given to me as f of x equals, if I plug in the opposite of x, I can see that when I take all of the operations into account, the opposite of x to the fifth power is still the opposite of x to the fifth. Negative 4 times the opposite of x is positive 4x. That is the opposite of the original function. If you can do that with a function, you've got an odd function. With an even function, when I do that exact same input, the opposite of x, what I'll see, and I don't want to use this word too broadly, but that the operations will cancel out, and I'm left with the exact thing that I started with. So the negative is now gone. If you're asked to test algebraically whether a function is even or odd, that's all you have to do. Plug in the opposite of x and see if you get the opposite of the original formula or the exact same thing as the original formula. For a function that is neither even nor odd, when you plug in the opposite of x, you will notice that neither one of those things happens. For this particular example, we'll see that the negative 1 inside the parentheses on the squared, the opposite of x times the opposite of x, it does cancel out and go away. So that part is back to the original. However, that does not happen with the x term in the middle. So this third function here is neither exactly the same as the original, nor is it exactly the opposite from the original when I plug in the opposite of x, or negative x. Now, we need to be careful not to get confused with our terminology here. Even degree, for example, polynomial, and even function are not synonyms. Just because you see an even power on your leading term does not mean that it's an even function. Odd degree and odd function are not synonyms either. So for example, we'll take a look at this non-polynomial function, x cubed plus x all over the absolute value of x. To plug in the opposite of x, I'm going to notice, first of all, make sure you're always putting these things in parentheses. That helps us remember our order of operations and such, and it helps us remember where negatives should cancel out and where they shouldn't. So what I see is that the numerator is going to become negative x cubed minus x, and the denominator is going to stay as the absolute value of x, because a negative inside the absolute value wouldn't really matter, would it? So I can factor out a -1 from the numerator, and I'm left with x cubed plus x over the absolute value of x. So this is an odd function. And that's not just because the numerator happens to have an odd power in it. There are all sorts of rules about what happens when I divide an odd function by an even function, for example. But it's not so simple as I looked at the degree and saw that it was an odd number. So, some quick brain teasers. Consider the following. The point 3, -7. Find the coordinates of a second point on the graph of the function f if the given point is on the graph and the function is even. So, let's draw ourselves a graph, and let's place 3, -7. If the function is even, then it would have to be reflected over the y-axis, which means we would also have to be able to find the point -3, -7. To look at this more algebraically, if I know that f of 3 equals -7, then changing to the opposite input should keep -7 as my output. For the second example, the same thing but odd, I need to look across my origin for a point here. -3, +7. So, the function evaluated at 3 gives me -7. For an odd function, taking the opposite of the input gives me the opposite of the output. Okay, half of the graph of an even function is shown. So what would the other half of the graph look like? Well, the other half of the graph would have to be a reflection over the y-axis for this to be even. So the graph in full would have to look like this. So here are 4 more example problems to try. You can pause the video, and first I'll put the answers up. Then I'll put the work up. Okay, here are the answers. Now pause the video, and I'll put the work up. I think the last one of these is the most interesting, and I think it provides us with a useful way we can tie in our previous knowledge. When I plug in the opposite of x in all of those places for the last one, I can see that the numerator stays exactly the same, but the denominator turns to the exact opposite of the original one. The same sort of thing as if you took 7/2 and changed it to 7 over -2. That would make the function its exact opposite, or in that case, I suppose, the number the exact opposite. All right, folks, I hope that was helpful. Have a great today and a wonderful tomorrow. I don't normally have a sign-off. And that's the wrong... Well, I'm not going to go back and edit this. I'll just have to put both audio attributions in the description. Have a good one.